Okay guys, so what as we seen last time, we have introduced algebraic structures, which is chapter 7, and we have seen that the algebraic structure means a set endowed with a certain operator, and this operator has got a property, and it is internal compositional law, which means that every time I take two elements from the set and I compose them, I get an element from the set. The second thing that we have seen has been semigroup, and semigroup is, it means that the operator is associative. Up to now it's quite easy. Then we have seen monoid. Monoid means that inside A there is a neutral element, which we have indicated with the letter E. Okay? So that's what we know up to now. And now I'm going to introduce a new kind of structure, if you like, or I'm going to give you this new definition, even though I know I have briefly given this to you already last time. But let's say a monoid of the type G dot is a group if all the elements inside G are invertible, which is traced, or which is represented in mathematics as that for all G belonging to G, there exists another element which we call G minus 1, which belongs to G, such that G by G minus 1 equal to G minus 1 by G equal to the neutral element. Okay? This is the definition of group, which is of course very important. Is this clear to everybody? I think so. Every element is invertible. And if you are new to my lectures, this symbol here is such that. Okay? Probably you have not seen this before, because it's something very local. But I tend to use it because I learned maths with this. But it's the same. Okay? And now I'm going to give you another easy definition. So, actually, the lecture of today is going to be somehow easy, well, relatively, and it is also done on purpose in order to give you a chance to catch up, because then next week is going to be tough, or a bit tougher. Definition. A group is abelian, is said to be abelian, or commutative if for all A and B belonging to G, it follows that B is equal to B A, which is something that is pretty obvious, I think. Commutative is something that we give for granted normally, well it's not. And we have already seen that, for example, if I take two matrices, A by B, is not equal to B by A. Do you remember this? Right. So in general, commutativity is a very special property. It happens only in some cases. Okay? And now this allows to introduce a property, let's say proposition here, and the proposition says, let us consider a group G dot if for all G belonging to G, it follows that G is equal to G minus 1. So if all the elements are equal to its inverse, then G dot is abelian. I give you first a proof because it's pretty easy. Then I try to give you an example and explain in depth what this means. Okay? So the proof is the following. Let us consider H and G elements of G. Are two elements. And I then calculate H by G. And since they are such that H is equal to H minus 1 and G is equal to G minus 1, then I can write that this is equal to H minus 1 dot G minus 1. Right? For what we have seen yesterday, for monoids, this is equal to G H O minus 1. Correct? It's what we have seen yesterday, if you take a different color. Yesterday we have seen, I think I used A and B yesterday, it's the same story. So that A minus 1 by B minus 1 is equal to VA O minus 1. And in general, I mean, I don't know, I cannot give for granted the commutativity, so I don't know what I'm going to do. Yeah? I can write only this, I cannot write AB minus 1. Do you remember this? Yes? You've seen? Well, if not, please look at the notes, look at the book, look at the video. So this, now we have some other thing. G by H is an element, and it is composed of G dot H. As such, this one, GH, is an element of the group because it is closed with respect to to dots. It's because this is an internal composition law, so this is an element of H. And then I know that every element an element of G, and that every element of G is equal to its inverse. Therefore, this is equal to GH. Right? So what did I write? I have written that AG and GH are the same thing. And that's the proof. Okay? So, now let us see what this means. I'm saying that if the group is very special, and it is such that every element is equal to its inverse, then the operator is commutative. In general, this does not mean that every time I have an abelian group, then the property is true, of course. Let us see one very special example of that group. So I'm picking up a group where every element is equal to its inverse. And the group is composed, we consider a certain set B, which is only composed of 0 and 1. It's a binary set. And then we consider the sum, as you would do in computer science, where, to make myself clear, 1 plus 1 is equal to 0. Right? So in this case, you have a set where essentially every element is equal to its inverse. Because, do you remember what the inverse element means? Do you? It means, so if I have A and if I have B, B is the inverse of A if A by B is equal to the neutral element, right? That's what it means. The neutral element here is 0. And that's what you got here, right? And that would be the same if you do 0 plus 0. Also 0. Okay? Fine. So, and in this case, plus is commutative. So that's what it means. But it does not mean the other way around. It does not mean that for all the abelian groups you have that every element is equal to its inverse. I mean, if we consider a certain, well, this abelian group, R dot, where dot is the multiplication, then of course this is abelian because it's obvious that whatever number I put, 2.3 multiplied by 4, is equal to 4 by 2.3. But it is not true that 4 is equal to 1/4. This is not true. Right? So, but if I have that special property, then it should be a billion. Okay. Fine. Now we can move to another property of groups, definition. And this property of groups is called cancellation law. Okay? And it says that if I consider a certain group G dot, and I consider 3 elements of G, which are A, B, and C elements of G, if A by B is equal to A by C, it follows that B is equal to C. Yeah? What you are probably thinking, C. Yeah? What you're probably thinking now is that this is always true. Right? That's what you're thinking, maybe. And that's an obvious statement. This is not true at all. The cancellation law is valid in some cases, but it's not valid in other cases. And I'll give you immediately an example to make the point. Okay, this one. Let us consider the matrix A 0, 5, 0, 5, and the matrix B 0, 4, 0, 4. And now we consider the matrix C 5, 0, 0, 5. Okay? And now we calculate A by B and C by B. Do you still remember how to multiply matrices? I hope so. So A by B, it means this row by this row, which means 0. Then we have this row by this column, which means 20.
0, 20, 0, 20.
Then, okay, 0, 20, 0, 20. What happens in this case? CB, we have 0, 20, 0, 20. Am I right? Okay. So we have that, of course, AB is equal to CB. Right? Can I then simplify this by removing this? No, I can't. The cancellation law is not valid for matrices. More specifically, it's not valid for R22, comma dot. In this case, the cancellation law is not valid. Then, when is the cancellation law valid?
Probably symmetric.
Sorry?
Probably symmetric.
The matrix is
Symmetric.
Yeah, I understand, but are you talking about matrices, aren't you?
Yes.
Well, I'm trying to say something slightly more general. And now, unfortunately, anyway, that's not really the answer, but you will get it in a second. I have to go through this proposition. And the proposition is that cancellation law, I don't know how you say that, is always valid for groups. Okay? Let us give a proof of this. Let us consider a group which is G dot. And we pick up 3 elements belonging to G. A, B, and C. They all belong to G. And then we write that AB is equal to AC. Okay? Since this is a group, it means, let us write this like this. Since G dot is a group, it happens that for all G belonging to G, there exists a G minus 1 inverse. Well, I will write everything. So this means that there exists an A minus 1 inverse of A. Okay? So,
It's meant to be AC equals AB equals AC.
yes, of course. Sorry about this. Yes, AB equal to AC. Then this means that I can, since this exists, I can write A minus 1 A B equal to A minus 1 A C, which means, of course, E. The E and the C look very similar in my writing, so let's write it this way. EB equal to EC. Okay? Which means that B is equal to C. Okay? Yes?
What is our set of for all values of G belonging to G that exists?
A G minus 1 inverse of G. I'm saying that that's a group, therefore every element has got an inverse. And what I'm telling you is that you can, when you apply the cancellation law from school, what you are implicitly doing is to apply an inverse. Let us see this. In practice, with a trivial example, I'm going to cancel this bit while I'm going to leave the matrices down. Okay, so let's imagine that you have this equation that is going to be, I don't know, 3x equal 5. Okay? And you have to find x. What do you do in this case? You simply say, yeah, I can write x is equal to 5 there. Right? But essentially what you're doing here is that you write 3 minus 1 multiplied by 3, x, equal to 3 minus 1, 5, by 5. This by this is going to be equal to 1, which is the initial element with respect to the multiplication. And so this becomes 1, which multiplies x, is equal to 3 minus 1, which multiplies 5. Or this can be, and this means 1/3, therefore x by 1 is x, and this is 5/3. So that's 5/3. That's what you implicitly do. Or if you prefer, what you do with the cancellation law is if you write something in terms of 3x equal to 3y, and then you conclude to say that x is equal to y, what you are doing here is to multiply this by 3 minus 1, 3x, and then here you have 3 minus 1, 3y. And then this becomes 1, this becomes 1, and then x is equal to y. Okay, this is a trivial thing, but that's what you implicitly do. And what I'm trying to tell you is that you cannot do that all the time. For example, in this case you can't. Why can't you do it? Which is somehow, we go to the comments that was coming before, which means why cannot I do this? Yes, please?
Because if you multiply the inverse of, say, b to ab, it wouldn't give you the same thing as if you multiply the inverse of b to cb.
I'm not sure I got to do it. So what I want to say is that
ab times the inverse
B minus
of b,
1.
yeah,
And here,
will not equal cb times the inverse of b.
well, actually, let us then make some kind of exercise. Will you be, what is b minus 1? Do you remember how to invert this matrix? You know what's the inverse? It's a 2 by 2.
It's not invertible.
It's not invertible. Therefore, this one does not exist. Therefore, I cannot write this equation because this is not existing. And that's all. So essentially, what I'm telling you is that R2 2 dot is not a group, it's a monoid. And the essence of a monoid is that not all its elements are invertible. You have some elements that are the non-singular matrices that are invertible, and some other elements which are the singular matrices that are not invertible. And in that case, so this means that in some cases you are going to be able to apply the cancellation law for matrices, in some other cases you can't. And since in general you can't, this means that you can't. That you cannot count on this. Okay, I hope that this was somewhat clear. This is kind of easy, but I would suggest you to not underestimate. And now that we know this, and we have also seen this thing here, I am ready to give you some examples. Okay. Actually, I'll give you a definition first, and then we give you some examples. Definition. Let us consider a certain group, G dot. We say that H dot is a subgroup of G dot if I can write this in 2 ways. The first way, which is the more synthetic one, is if H is a subset of G and H dot is a group. Or, equivalently, I can say if H is a subset of G, if because I lose the focus of what I'm saying. If dot is closed, if H is closed with respect to dot, and if the neutral element is contained in H, and if for all H belonging to H, there exists an H minus 1 such that H by H minus 1 equal to H minus 1H equal to the neutral element. So this is of course a little bit more extensive definition, but it's just summing up what we have already seen. This means H is closed, so that I have G, I consider a subset of G, and when I take 2 elements of H, and I multiply one by another, I operate them, then I get an element of H. Now, the neutral element of G is also contained in H, and that every element of H is also invertible. That's what makes a subgroup. Now, to start yourself to make examples of groups and subgroups is going to be a difficult thing. What I'm going to do is somehow to guide you through, to give you a couple of examples, and I expect that you know those 2 or 3 examples, okay? So, at first, let us try to do a little exercise together. And we consider, well, we start very slow, let's do then this. Let us consider the most typical group that we might think, R dot. This is a group. You agree with me? Yeah. It's a group because, because it's closed, because it's associative, because it has neutral elements, and because every element in R is invertible. Now, I consider this interval, minus 5, 5, dot, and I ask you, is this a subgroup or not? We can look at the definition, so we have somehow to assess whether or not this is a group. At first, we look, does it contain the neutral element?
Yes.
Yes, it does, because 1 is inside that interval. Fine. Can I invert every element of this interval. So if I take element 3, then I have also 1/3. If I have -2, I have -1/2, and so on.
Yes.
So that will be fine. But if what happens if I take 5 and then multiply it by 4? I get 20. And 20 does not belong to -5/5. This is not a subgroup. Okay? Why? Or how do we say in maths? Because this structure here is not closed with respect to the multiplication. Okay? I am going to give you now another example of a group and a subgroup. Actually, I'm going to give you two examples. So these are important. You need to know these two. That's somehow, that's the deal that I am making with you. I'm giving you two examples. You need to learn these two. So the first one is, we consider Z plus. We can easily see, and somehow we have seen this yesterday, that that's a group. And now, I consider Z5 plus. Okay? Where Z5 is essentially all the elements of Z multiplied by 5, which means whatever comes here, -10, -5, 0, 5, 10, 15, and so on until infinity. Okay? For how this is built up, even though we are dealing with infinite sets, but still we can say that Z5 is a subset of Z. Yeah? Because all the numbers that are in this set over here are also numbers of this set. Then we say, let's do this one that is easy. The neutral element of this one is 0. 0 also belongs to Z5. So we are fine. Okay? The next bit that I have to check is if every element over here is invertible. Well, if I take, for example, 5, then I have also -5. If I take 10, I have -10, and so on. So I can always sum up two of the, for every number I can find here, I can always find another number inside here, such that when I sum them up, I get 0. Do you understand the statement? Right. So, all the elements are invertible. And now, I have to check that it is closed with respect to the sum. If I add 5 to 10, I get 15, which is inside. If I take 15 plus -5, I get 10, and so on. So every time I take two numbers over here, I get a number inside Z5. Therefore, this is closed with respect to the sum. This means that this is the first example that you see of a subgroup. I mean, I'm clearly building up on the theory. Eventually, you will see why I'm doing all this. I am starting to introduce one thing in order to look at one property of the groups, which is called the Lagrange theorem. But I need to arrive at it, and it's gonna take me until the end of the next week. Okay, the next example that I have is this one. I'll start with at first with the general one. We consider Z12 plus 12. Now I have to explain you what this is. Z12 is let's see. Okay, is Z12 is a set of integers which has 0, 1, 2, 3, and so on until 11. Okay? And plus 12 is the so-called cyclic sum. What does this mean? It means that essentially when the sum of these two numbers is 12, then it is 0. When it is 13, is 1, and so on. So for example, if I do 11 plus 3, this would mean 2. Okay, oh, sorry, plus 12. Yeah? Did you get me? You understand how it works? So for example, 5 plus 12, 2 is going to be 7, but 5 plus 12, 10 is going to be what? 3. So whatever comes here, then you have to take 12 of every integer that comes proportional to 12 out. So, well, let's say that you have to take, when you have only two numbers, you have to take out only 12 if it exceeds 12. So that essentially, it's called cyclic because what you see is that 0, 1, 2, 3, 4, and so on, until 11. It's a bit like, works a bit like a clock. Right? It's I guess it's kind of easy. Now, what is less easy is let us show that this is a group. Now, first bit. To show that this is a group, we have to make a first consideration. Is this an algebraic structure? The answer is yes, because as you can see, when I sum two of these numbers, I always get a number that is between 0 and 11, right? So, yes please.
What if you do 0 plus 11?
0 plus 11 will equal to 11.
No, but using the 12 cyclic sum.
Yeah?
It's still okay.
Because the sum is less than 12.
Yeah.
Okay? And so we decided that this is an algebraic structure, and essentially this comment allows me to say that 0 is the neutral element. I appreciate you're tired. Did you have a long day before? Have you had many hours before this one? No. I mentioned, do you have just, is this your first hour of the day?
No, we have a 4-hour break.
4 hours break?
Yeah.
Wow, okay. Okay, it's interesting. So maybe this room is not available, that's why. Because I'm available on a Thursday morning.
We were here from 1 to 2.
Yeah, we were in everyone.
Okay, I would continue, we can speak about this later, how we are recording. So do a cyclic sum, sorry, and the 0 is the neutral element, and we can easily see that this is associative. And the other thing that we have to see is that every time I pick up, let's say that I pick up a certain number here, let's say I pick up 2, can I find another number such that, can I solve this equation, plus x equals 0? Can I do that? Can I always find it? What would be the solution here? 10. Right. So, I can always find this. This means that this is a group. It means that for all element G belonging to Z12, there exists an element G1 inverse of G. So, this story here is to say that this is a group. Now that we have convinced ourselves that we are dealing with a group, we have now the opportunity to build up a subgroup. And the subgroup that we are going to build up has to be a subset of Z12, and it has to use this same operator and still has to be a group. And what I'm going to take is the following one. 0, 2, 4, 6, 8, and 10. I'm going to call this H, and now we have to show that H plus 12 is still a group. Can you see that that's still a group? Very quickly, you agree with me that you can sum two of them and you get something that is inside the set, right? Then you can see, you agree with me that 0 is inside the set.
Yes.
Then you probably, well, you still this is associated. And you probably agree with me that if I take any element here, I can always find another element that is, or one element from this group that is its inverse. Let us pick up at first this. What will be the inverse in this case? 4, and 4 is here. And if I take this one, it will be 6. So in this case the inverse is 6, in this case the inverse is 4. So this is a group, therefore this is a subgroup. Right. Again, if I ask you to invent a subgroup, to come up with an example, that would be difficult. If you try to think, you're going to struggle to find something. But what I expect for you for this module is that you learn these two, and that you understand these two examples, okay? Well, that one and this one. Now, I have to give you the last definition of the day and of the week, which is gonna look very strange to start with. But bear with me, eventually it will make a little bit more sense. I don't know how much more, but a little bit more at least. And this is going to be, it's going to be a little bit odd, but okay, definition. Let us consider a certain group, G dot. So this is a group. And let us consider H dot subgroup. Okay, we say that a coset is a set built up from the group and its subgroup. And it is indicated this way, HG. Okay? And it is defined as, let me say first, G. Let us consider G as an element of G. And this is the set of all H dot G, such that H is an element of H. This is very unfriendly, but it's probably less difficult than what it looks like in the first place. What does this mean? It means that I pick up one element from the set, G, I pick up all the elements of H, and I perform the operation of this element, well, this element, or let's say, yeah, this element by this other element, not in this order. So, for example, I can, here I have a group, and here I have a subgroup. In order to build up an example of coset, I pick up G elements of Z12, and I choose G equal to 1, okay? I pick up one element. And then I have all the set H, and all I have to do is to build up HG, I need to do 0 plus 1, 2 plus 1, 4 plus 1, of course this is plus 12, yeah? Plus 12, plus 12, plus 12. 4, 6 plus 12, 1, 8, plus 12, 1, 10, plus 12, 1. And I end up with 1, 3, 5, 3, 5, 7, 9, and 11. Okay? This looks odd, fine, but you did understand this example for now? And we are happy for the time being. Two considerations, or at least one consideration that is important, is that, well, a group is a set with an operator. A subgroup is a group, therefore is again a set with an operator. A coset is just a set. And so there is no operator, and there is no requirement that there's a group, that there is like the initial element and so on. It's just this odd set that is built up from a group and subgroup together somehow. Is this somehow okay up to now? Fine. And I think, well, let me say just a very, very last thing, just for completeness, that it's just a very last thing. This is HG, but I could also build GH, where here we have GH, H element of H. And in this case, let's say in one of these cases we call this as a left coset, and then the other case this should be the right coset. Okay, so this should be left, and this should be right. I hope I'm not saying it's not the other way around. But for what is relevant, let's say that we are going to focus only on this. It doesn't matter. We focus only on one because all the examples that we have made are actually commutative. Therefore, these two are the same. Okay? Because if you do, essentially, the difference will be that instead of 0 plus 1, you have 1 plus 0, 1 plus 2, and so on. Which in this case is the same. So it doesn't matter. So for this module, it doesn't really matter. Thank you very much. I'll see you next week.